You know, the world is just swimming in data these days. We're practically drowning in petabytes of transactional history, click streams, sensory output, you name it.
Absolutely. It's staggering.
And if you're building anything at scale in, well, 2024, trying to make sense of this colossal flood of information, there's like, what, an 80% chance you're using the engine that basically powers the Fortune 500? Apache Spark.
That's the one.
So, welcome everyone to this deep dive. Today, we're stepping beyond just writing the code. We want to learn the subtle art of data bending.
I like that term, data bending, because Spark really is the undisputed heavyweight champion for big data processing. But here's the thing you hit in production environments, right? Running Python or Scala code on Spark, that's actually pretty easy to get started with.
Right.
Getting that code to run fast, now that's the challenge. To achieve that, lightning fast performance, you need to become a true data bender. You got to manipulate the data flow, the execution plan, the cluster resources, really bend them to achieve maximum efficiency.
And that right there is the obstacle course, isn't it?
Yeah.
You're dealing with the inherent complexity of distributed computing, machines talking across networks, failures, mixed with this, frankly, daunting configuration challenge. Our sources kept highlighting this. Spark has over 180 configurable parameters. I mean, if you're manually searching for the optimal combination in that landscape.
Forget it. You'll never finish. It's just too vast.
Exactly.
So our mission today is to cut through that complexity. We've really dug into the deep research, the essential engineering wisdom, the shortcuts to mastering Spark. We're going to show you how to conquer data movement, that notorious shuffle.
Ah, the shuffle.
Yeah, how to master configuration tuning, and how to implement these modern optimization strategies that can seriously turn a job that takes hours into one that takes minutes.
Okay, let's unpack this then, starting right at the beginning with the fundamental architecture. How does Spark even get to work in the first place? So when people first approach Spark, I think there's a tendency to treat it like just one super powerful computer. But the secret sauce, as you said, is that it's inherently distributed. It's like a symphony of nodes all working together.
That's a great analogy.
Can you walk us through the anatomy of a Spark cluster? Like, who are the main characters in this play?
Definitely. So think of the Spark cluster as this massive automated factory floor, right? But for data, you have two absolutely critical roles. First up, you've got the driver.
Okay.
This is the application's central control unit. It runs your main function, it maintains the overall state of your application, and crucially, it acts like the conductor of that orchestra you mentioned.
The conductor, right.
It takes your massive workload and orchestrates exactly how it should be broken down into smaller parallel tasks. And it's critical. If the driver fails, the whole application stops. The brain is gone.
So the driver's giving the orders, kind of directing traffic, but the actual heavy lifting, that's done by the workhorses.
Precisely. Those are the executors. These are the worker processes. And they live on the individual machines, physical or virtual, scattered across your cluster. They're the ones actually receiving those tasks from the driver, performing the computation on their specific slice of the data, and then reporting the results back.
And this is where Spark gets its speed advantage, right? The in-memory part.
Exactly. The reason Spark just dominated so quickly, its impressive efficiency, it stems directly from how these executors use in-memory caching. By keeping those intermediate results in fast RAM, instead of constantly writing them back to slow disk like older systems, it just dramatically speeds up iterative processing, machine learning loops, sequential operations, all that stuff.
So the power of the cluster is one thing, but it's matched by let's say, the intelligence of its core strategy. You mentioned the catalyst optimizer and lazy evaluation. For the user just writing the code, what's the immediate painful trap that lazy evaluation helps them avoid?
Oh, lazy evaluation is Spark's way of basically saying, hold your horses. Like, wait a minute.
Okay.
When you define a transformation, say a filter operation, or maybe you add :Spark, doesn't actually execute that code right away. Not instantly. Instead, it meticulously builds up this abstract execution blueprint. It's called the Directed Acyclic Graph, or DG. It only kicks off the actual computation when you call an explicit action, something like collect, or write, or count.
So it builds the plan first.
Right. And the trap it avoids is premature execution, running things before it knows the whole picture.
Okay, but why is waiting so powerful? It feels counterintuitive. Don't you want it to start working immediately?
Well, because by waiting, Spark gets to look at the entire sequence of operations you've defined, everything, from reading the raw data all the way to the final output. And then it can figure out the globally most efficient way to run the whole thing end to end. It can effectively rewrite inefficient user code behind the scenes.
Ah, okay, so it sees the whole chain of commands.
Exactly. And you mentioned a classic aha moment earlier, predicate pushdown.
Yeah, we often hear people talk about free optimizations in Spark. Is that what this is? Can you elaborate on that one?
Predicate pushdown is pretty much the definition of a free optimization. Let's say you write a query, maybe in Stark SQL, to filter a huge Parquet table like where date 2023-0101.
Okay.
Spark's Catalyst Optimizer is smart enough to push that filter condition down to the data source itself, the Parquet reader in this case. So instead of reading all 10 years of the data into memory and then filtering it,
Which would be hugely wasteful.
totally wasteful,
Wow.
it instructs the Parquet reader to only load the data blocks that actually correspond to 2023 and onwards. You might have just avoided reading, say, 90% of your data simply because you were lazy, or rather the system was, and let it optimize the plan before execution.
That's pretty clever. And that heavy lifting, that optimization work, that's the job of the Catalyst Optimizer. You said it sounds like some kind of highly evolved data architect. It has, what, 6 steps? What are the really high-stakes decisions happening inside that black box?
It is, yeah. It's a really sophisticated process. It moves from this abstract idea of your query to the physical reality of running it. It starts step 1 with the initial logical plan. That's just your raw query parsed syntactically.
Just the code you wrote.
Pretty much. Step 2 is the resolve logical plan. Here, it checks everything against the metadata catalog. Are the column names valid? Do the schemas match up? Basic sanity check.
Make sure it's not nonsense.
Right. Then comes the real intellectual heavy lifting, the optimized logical plan. This is where logical rules get applied. Things like combining 2 consecutive filter operations into a single one, or applying that projection pushdown we just talked about, figuring out which columns you actually need.
So it's cleaning up the logic, making it smarter before it even thinks about how to run it physically.
Exactly. Next, step 4, it generates multiple physical plans. So it thinks, okay, there are several ways I could actually execute this optimized logic. Should I use a hash join for this step? Or maybe a sort of merge join would be better given the data sizes. It comes up with several viable strategies. Options, right? These plans are then fed into step 5, the cost model. This model estimates the cost or expense of each of those physical plans. It calculates things like estimated CPU cycles, how much data needs to be shuffled across the network, a big one, and the I/O required.
It's trying to predict the pain points.
Precisely. And Catalyst's ultimate job, step 6, is best plan selection. It evaluates the costs and picks the plan it predicts will be the most efficient, the cheapest to run. The cool thing is how flexible Catalyst is. It manipulates these abstract plans using both rule-based logic and this cost-based estimation, which makes Spark really adaptable to different data sources, cluster setups, all sorts of things.
And a huge part of that decision-making, figuring out the cost, it seems to hinge entirely on how much data needs to move around. Which brings us to how we categorize the operations we write. Narrow versus wide transformations. You said this is fundamental.
Oh, it truly is. This distinction basically determines whether your operation is going to be fast and can be pipelined, or if it's going to be slow and require a resource-intensive stage break in the execution.
Okay, break down narrow first, the efficient ones.
Right. Narrow transformations are the good guys, performance-wise. They have a simple dependency. Each input partition, so each chunk of data on an executor, contributes data to only one output partition. Think about applying a map function, or a filter, or even union. The key is, the data generally doesn't need to leave its original executor to compute the result. It stays local.
Like your filter example, I tell worker A to keep only the blue records, and those blue records just stay right there on worker A. The computation happens in place, in memory.
Perfect analogy. And because of that, Spark can perform these via pipelining. It can run multiple narrow operations back to back, all in memory, without having to stop and save intermediate results to disk or send them across the network. Super efficient.
Okay, so what about the other side? The wide ones, the performance killers.
Yeah, wide transformations. These are your potential performance killers if you're not careful. Here, an input partition contributes data to many output partitions. Operations like group by key, reduce by key, repartition, or most types of join operations fall into this category.
Because data from different places needs to come together.
Exactly. This forces a cluster-wide data exchange. And that exchange is the infamous shuffle.
The shuffle. And crucially, this wide transformation, the shuffle, it forces the transition from one stage to the next in that DAG blueprint you mentioned. Can you clarify that distinction? Yeah. Stages versus tasks.
Good point. The DAG is the overall blueprint for the entire job, right?
Right.
Stages are like large phases within that execution plan. And they are separated specifically by wide dependencies, meaning by a shuffle. A wide transformation acts as the boundary marker. It forces Spark to complete all the operations in the current stage.
Finish everything up to that point.
Yes, finish everything, potentially write the intermediate results, and then move the data around the cluster to start the next stage. Now, within each stage, you have multiple tasks. A task is the smallest unit of work. It often corresponds to processing a single partition of data on a single executor core.
So one chunk of data, one core.
Typically, yes. If you have, say, 100 partitions of data being processed in a stage, you'll likely have 100 tasks running in parallel across your executors. But the moment you hit a wide transformation, you stop that current set of tasks, you physically move the data that's the shuffle, and then you kick off a whole new stage with a new set of tasks operating on that newly rearranged shuffled data. And it's that movement, that physical data exchange, that makes it so costly.
Okay, let's dive deep into the shuffle then, because honestly, this seems to be where most performance bottlenecks live, right? If you look at your Spark UI and see huge shuffle reader write times, you know you've got a problem.
Absolutely. It's usually culprit number one.
We know it eats up network bandwidth and CPU cycles, but you mentioned something earlier, the reliance on disk I/O seems particularly painful. If Spark is supposed to be this great in-memory engine, why does it have to write all this intermediate data to disk during a shuffle? That feels like a contradiction.
Yeah, it does seem counterintuitive, doesn't it? But this takes us right back to fault tolerance, which is absolutely critical when you're dealing with massive distributed systems where things can and do fail.
Okay.
Imagine you have a stage, let's say stage 1, that takes 30 minutes to run. It produces a whole bunch of intermediate results that are needed for the next stage, stage 2. Now, what happens if one of your executor machines fails halfway through running stage 2?
Uh-oh. You lose the work it was doing.
You lose the work. And you might lose the intermediate data it needed if that data was only held in that failed machine's memory. If the shuffle data was purely in memory, the failure of just one machine could force Spark to go all the way back and rerun the entire 30-minute stage 1 for all the data, just to regenerate the input needed for the failed part of stage 2. That would be disastrously inefficient.
Okay. So the disk, right? The shuffle persistence, as they call it, writing those intermediate files to local disk. It's basically a performance trade-off. You take a hit writing to disk, so you gain reliability.
Exactly. It's an insurance policy. Spark writes those shuffle files to the local disk on the executor nodes that produce them, the map side. If downstream task, the reduced side in stage 2, fails, the data it needs is safe and sound on the disk of the executor from stage 1. This allows Spark to just relaunch the specific failed task in stage 2, reading the necessary data from disk across the network without having to rerun the entire, potentially very long predecessor stage. But yeah, that disk write, followed by the network transfer to pull the data where it's needed, often involving gigabytes or even terabytes of data, that's precisely why the shuffle consumes such vast resources. Disk I/O, network bandwidth, CPU for serialization, deserialization, the works.
So the golden rule really is avoid unnecessary shuffles whenever you possibly can. Bend the logic to prevent them.
That's rule number 1, 2, and 3 of Spark tuning.
But okay, even when a shuffle is necessary, like you absolutely need to do a group B or a big join, you still have to manage it correctly. You mentioned the default shuffle partition size is 200. Why is the seemingly arbitrary number spark.sql.shuffle.partitions 200 so often a source of inefficiency? Seems like a reasonable default.
It seems reasonable, but it often creates a tremendous amount of overhead, especially with smaller or moderately sized data sets. The setting spark.sql.shuffle.partitions literally tells Spark how many output partitions to create after a shuffle operation.
Okay.
Now, imagine you run a job, and the actual data volume being shuffled only naturally results in, say, 10 partitions worth of meaningful data. But your setting is still stuck at the default 200.
What happens?
Spark will dutifully try to divide that output across 200 potential files or partitions. What you end up with is maybe 10 files that have actual data and 190 tiny, maybe even empty files.
Wow, okay. That sounds like a mess.
It is, because managing 200 files, tracking the metadata, opening connections, closing connections, the scheduling overhead for 200 downstream tasks, even if most do nothing, is far, far more costly and inefficient than just managing, say, 10 or 20 appropriately sized partitions.
So what's the goal then? How do you figure out the right number?
The goal is to have partitions that are reasonably sized. A common rule of thumb, or maybe a target, is somewhere between 128 milbits and 256 milbits per partition after the shuffle. If you have partitions that are much smaller, you get that overhead problem. If they're much larger, like over a gigabyte, you risk running into memory issues within a single task, like out-of-memory errors, and you might not be utilizing the parallelism of your cluster
So
effectively.
you need to estimate the size of the data being shuffled before setting the parameter.
Ideally, yes. Let's say you estimate you'll be shuffling around 100 gigabytes of data. If you use the default 200 partitions, each partition would be 100 gigabytes, 200 equals 500 gigabytes. So maybe a bit on the large side, could cause memory pressure.
Yay.
If you aim for, say, 128 millibyte partitions, 100 gigabytes is roughly 100,000 millibytes. So 100,000 millibyte, 128 MB partition gives you around 780, 800 partitions. So setting Spark.SQL to shuffle partitions to maybe 800 in that case would likely lead to much better performance and stability than the default 200. That calculation, or at least estimation, is really key.
Okay, that makes sense. Moving from the data structure side of things to the machines themselves. Let's talk resource bending through configuration. We mentioned the 180 plus parameters. It's clearly impossible to tune all of them manually, but what are like the absolute critical knobs we must get right?
Yeah, if you had to pick just a few, you absolutely have to focus on memory. Memory, memory, memory. And related to that, how you allocate CPU cores. The really critical parameters usually involve the driver memory, spark.driver.memory, the executor memory, spark.executor.memory, the number of cores per executor, spark.executor.cores, and maybe the number of executors, spark.executor.instances, although dynamic allocation helps here.
Let's take spark.executor.memory. Intuitively, you'd think more memory is better. Give it as much as the machine has.
That's the common intuition, definitely. But the research and practical experience points to this really fascinating paradox. Over-provisioning memory, giving it too much, can actually degrade performance, sometimes significantly.
Wait, how does giving the machine more resources slow it down? That seems completely backwards.
I know, right? It's a classic distributed system, or maybe more specifically a Java virtual machine, a JVM issue, since Spark runs on the JVM. If you give an executor a huge amount of memory, say 32 GB or 64 GB, well, JVM itself needs significant overhead just for its internal bookkeeping, thread stacks, memory safety buffers, all that. But the killer is garbage collection, or GC.
GC pauses, the bane of Java performance.
Exactly. The larger the JVM heap size of the main memory pool, the longer the potential garbage collection pauses become when the JVM needs to clean up unused memory. And when the JVM hits a big stop-the-world GC event, your entire Spark task on that executor just pauses, completely frozen while memory gets cleaned up.
And those pauses add up.
They add up massively. A few long GC pauses, maybe lasting seconds each, can easily wipe out any theoretical benefit you thought you were getting from having all that extra memory available for caching. The task just sits there, doing nothing productive.
So we're balancing the need for decent memory for Spark's caching against the inherent slowdown caused by the JVM trying to manage that huge memory space. What's a good rule of thumb, then, for configuring executors? Is there a sweet spot?
There tends to be, yeah. A strong industry best practice often cited is aim for around 5 concurrent cores per executor. Spark.executor.cores 5. If you try to cram too many cores onto a single executor JVM, you start getting heavy contention for shared resources within that JVM. Things like shared memory structures, maybe even contention on the network card interface or local disk I/O if tasks are heavy on that.
So too many cores fighting over the same internal JVM resources.
Right. And for memory, pairing those 5 cores with maybe 4 GB to 8 GB of executor memory, spark.executor.memory, 4G to 8G plus some overhead, is often a very good starting point. It seems to balance parallelism across cores, keeps the JVM heap size reasonable enough to minimize those long GC pauses, and generally utilizes the cluster hardware pretty efficiently. The key takeaway is the goal isn't the maximum possible resource allocation. It's the optimal configuration, the one that maximizes throughput by balancing parallelism and minimizing interference and overhead like GC.
Okay, optimal, not maximal. Got it. And how do modern systems handle the fact that workloads often vary? You know, I might run a small report at 9 a.m., but then a massive ETL pipeline kicks off at 5 p.m. Manually changing settings all the time sounds tedious and error-prone.
Absolutely. And that's exactly where dynamic allocation really shines. It's a fantastic feature. It allows Spark basically to dynamically request and release executors based on the actual workload it sees.
So it scales up and down automatically.
Pretty much. If a particular stage of your job needs, say, 50 executors to process all its tasks in parallel, Spark can request those from the cluster manager, like Yarn or Kubernetes. Then, crucially, when the work for those executors is done and they're sitting idle, Spark can release them back to the cluster pool.
Ah, so they don't just sit there wasting resources.
Exactly. This maximizes resource utility across the whole cluster. It's especially important in multi-tenant environments where maybe other teams or applications are waiting to use those resources.
Hmm.
When your job doesn't need them, they get released, allowing other applications waiting in the queue to grab them and run. Much more efficient use of expensive hardware.
Okay, let's switch gears a bit and talk about a problem that isn't about configuration but inherent to the data itself. Data skew. You could have perfect resource allocation, perfect partitioning strategy, but skew can still just turn a 10-minute job into a 10-hour nightmare. What does this look like in a real-world scenario?
Oh, data skew is brutal. It happens when your data is really unevenly distributed across the keys you're trying to join on or group by. Imagine you're joining customer transaction data with customer profile data. Maybe 99% of your customer IDs are unique and have a reasonable number of transactions.
Okay.
But you have one specific ID, maybe it's guest use or unknown customer, and this single key value actually represents like half of your total transaction volume.
Right, like anonymous checkouts or something.
Exactly. So when Spark performs the shuffle for the join or the group by operation, all the records for that one massive key, guest user, are going to get sent to the same single partition. And therefore, they land on one single executor task.
And that task gets totally swamped.
Totally swamped. It becomes the straggler. You'll see it in the Spark UI 99 or 199 other tasks finish in minutes, and they're just sitting idle waiting. Meanwhile, this one poor task is chugging away for hours trying to process that mountain of data for the single skewed key. The whole job is bottlenecked by that one task.
So we have this bottleneck that's just baked into the data itself. How do we bend the data to fix this before the join happens and creates the straggler?
This is where we get into some clever manual data manipulation. The most common technique is called the salted join technique. It's a way to artificially break up that one massive key.
Salting, like adding salt to food.
Kind of. The strategy is, first, you identify the skewed key, in our example, guest usser. Then you artificially distribute its records by adding a random salt value. You introduce a synthetic random component to the key just for the skewed values before the join.
How does that work? Give me an example.
Okay, so for all the records where the key is guest usser, you might append a random number, say from 0 to 9, to the key. So the original single key guest usser now temporarily becomes 10 different keys, guest usser 0, guest usser 1, guest usser 2, all the way up to guest usser 9.
Ah, so you're effectively splitting that one huge pile of records into 10 smaller, roughly equal piles. You're temporarily distorting the data just to make it parallelize better.
Exactly. That's the core idea. Since the records for the originally skewed key are now spread across these 10 new salted partitions during the shuffle, the workload gets distributed much more evenly across, say, 10 different executor tasks instead of choking just one.
Okay, that makes sense for the big table. But what about the other table you're joining with, the smaller one?
Good question. You have to handle that too. You need to modify the corresponding keys on the other side of the join to match the salt. The common way is to essentially duplicate the records for the corresponding key on the smaller table, or the dimension table, 10 times, applying each salt value, 0 through 9, to one copy.
So you replicate the small table's matching record 10 times, salted.
Right, so that guest usser from the big table can find its match, guest usser 1 can find its match, and so on. Once the join operation itself is completed, now much faster because it was balanced, you then typically remove the synthetic salt component from the key, bring it back to the original guest usser, and you're left with the correct joined result, but you achieved it without the massive straggler problem.
Yeah.
It's definitely a more advanced manual intervention, but sometimes it's the only way to overcome severe data irregularity.
Okay. Now we're getting into what you called precision techniques. These feel like the more subtle optimizations that can really turn a slow pipeline into, well, a rocket ship. Let's start with bucketing. This sounds a bit like partitioning, which we discussed earlier, but the sources indicate it provides a much deeper sort of physical optimization. How does it work differently?
Yeah, they sound similar, but they operate at different levels. Partitioning, like we said, is usually higher level. It physically splits your data into different folders based on a column's value, like year 2024, country US, that kind of thing. It helps prune entire directories during reads.
Right, filtering folders.
Bucketing is more granular. It operates within those partitions or sometimes instead of partitioning on low cardinality keys. It's a physical optimization where data is grouped into a fixed number of buckets based on the hash of a specific column key, say customer. You decide up front, I want 100 buckets.
Okay.
Then, for every record, Spark calculates a hash of the customer id, takes the result modulo 100, so hash customer percent of 100, And based on that remainder, 0 through 99, it places the record into a specific numbered bucket file within the partition directory.
So it's distributing rows based on a hash calculation into a fixed number of files. Why is this deterministic grouping so powerful for performance, especially, I think, for joins?
Because it provides a guarantee of co-location for the join keys. This is the primary benefit. It allows Spark, under the right conditions, to completely avoid that expensive shuffle during a subsequent join operation.
How does it avoid the shuffle?
Okay, imagine you have two large tables, Table A and Table B, and you need to join them on custom read. If both Table A and Table B have been saved using bucketing, using the same number of buckets, say 100, and bucketed on the same key, custom read, then Spark knows something crucial. It knows that any records for a specific custom read, say custom read equals 1, 2, 3, 4, 5, must reside in the same bucket number, let's say bucket 42, based on the hash in both tables.
So all the matching keys are guaranteed to be in corresponding files already.
Exactly. So Spark doesn't need to shuffle data all over the cluster to bring matching keys together. It only needs to read bucket 42 from table A and bucket 42 from table B on the same executor, or maybe just a few executors, and perform the join locally. It can completely skip the network-intensive shuffle phase for that join. It's an enormous efficiency gain, essentially bypassing the most expensive type of wide operation. It requires planning when you write the data, but pays off hugely when you read and join it later.
That's clever. Okay, speaking of joins, let's talk about what seems like the most critical optimization for just day-to-day Spark work. The big versus small rule. This translates into the broadcast join. If I have, say, a massive 1 terabyte fact table, and I need to join it with a relatively tiny 5 megabyte dimension table, what absolutely must I do?
You absolutely must ensure Spark uses a broadcast hash join. This is pretty much non-negotiable for good performance in this scenario. The goal, again, is to eliminate the shuffle entirely.
Okay, how does it work? How does broadcasting eliminate the shuffle?
The mechanism is conceptually simple. Spark takes the small table, that 5 MB dimension table, collects its entire contents onto the driver node, and then literally broadcasts or copies that complete small table out to every single executor node in the cluster.
So every worker gets its own local copy of the small table.
Precisely. Now, when the join operation runs, the tasks processing the partitions of the massive 1 TB fact table don't need to shuffle data. They can simply perform the join against the complete copy of the dimension table that's already sitting right there, locally, in memory on the same executor. It's typically a very fast hash join performed locally. This avoids all the network I/O, sorting, and merging associated with a shuffle join.
That sounds fantastic. Almost too good to be true. But there's a serious catch, right? A danger zone if we misjudge the size of that small table.
Oh, absolutely. This is a high-stakes moment where things can go very wrong very quickly. By default, Spark has a configuration parameter, spark.sql.autoBroadcastDrain threshold, typically set around 10 millibeat or maybe a bit higher in newer versions. If a table involved in a join is estimated to be smaller than this threshold, Spark will automatically try to broadcast it.
Okay, so it tries to be smart.
It tries. But sometimes the statistics might be off, or you know the data better, so you might manually force a broadcast using a hint in your SQL or code, like select plus broadcast, small table.
Right, you overread the default.
Exactly. But here's the danger. If you force a broadcast on a table that you thought was small, but it turns out to be, say, 500 millibeat or even 1 GB, you could be heading for disaster.
Why? What happens?
Because the driver node, remember, the central coordinator is the one responsible for collecting the entire table that's being broadcast before it can distribute it out to all the executors. If that table is too large to fit into the driver's allocated memory, spark.driver.memory, the driver will likely run out of memory and just crash instantly.
The whole application just dies.
The whole application dies. I personally saw an engineer once bring down a production Spark application running on a driver node with like 64 GB of RAM because they tried to force broadcast a table that was maybe just 100 millibeat or 200 beat or larger than the driver could handle in memory after collecting it. The system just seized up, kaput. So the lesson is, always know the approximate size of your data before you manually force a broadcast hint. Use it with caution.
Yikes. Okay, noted. So for those unavoidable situations where both tables are genuinely large, the big versus big scenario, Spark can't broadcast. What does it default to then?
When both tables are large and broadcasting isn't feasible, Spark typically defaults to one of two main strategies. Either a shuffle hash join, which involves shuffling one or both tables based on the hash of the join key, or quite commonly, a sort merge join.
Sort merge join? That sounds potentially slow.
It often is the slowest option because it involves multiple expensive steps. First, it has to shuffle both large tables, partitioning them by the join key. Then, critically, within each partition on each executor, it has to sort the data based on the join key. Finally, once both sides are sorted, it can efficiently merge scan through the sorted partitions to find the matching keys. But that sort step, especially on large partitions, can be very costly in terms of CPU and potentially disk I/O if data spills.
Okay, so broadcasting is great for big v small, but big versus big often means a costly shuffle and maybe a sort. This seems like a perfect lead-in to perhaps the most modern and sophisticated technique for handling these kinds of runtime ambiguities, adaptive query execution, or AQE. How does AQE change the game by optimizing things mid-job?
AQE is, yeah, it's like Spark getting smarter while it's running. It really takes the optimization process beyond just the initial planning phase, compile time, and brings it into the runtime execution phase. It starts with the initial physical plan that Catalyst chose, but then it dynamically monitors and adjusts that plan during execution based on the real-time statistics it gathers as the job progresses.
So it's not locked into the first plan, it can change its mind.
Exactly. Instead of rigidly sticking to the plan made with potentially stale or estimated statistics, AQE remains flexible. It can react to what's actually happening with the data sizes and distributions as they flow through the day.
That sounds powerful. What specific problems can this dynamic flexibility, this runtime adaptation, allow Spark to tackle that it couldn't before AQE?
It enables several really crucial optimizations that were previously impossible or required manual intervention. First, AQE can dynamically optimize join strategies. Imagine Catalyst initially planned a sort-merge join because the table statistics before the job started indicated both tables were large.
Okay.
But maybe, due to filtering steps earlier in the job, by the time the data actually reaches the join operator during execution, AQE observes that one of the tables has become much smaller than expected, small enough, perhaps, to fit within that broadcast threshold. AQE can then dynamically switch the join strategy mid-job from the planned sort-merge join to a much faster broadcast hash join on the fly. That's huge.
Wow, okay, what else?
Second, it dramatically improves partition management, especially after shuffles. Remember our discussion about the default 200 shuffle partitions, often creating lots of tiny files?
Yeah, the overhead problem.
AQE can automatically coalesce small shuffle partitions. As the shuffle completes, AQE looks at the actual sizes of the resulting partition files. If it sees, say, 200 physical files were written, but maybe 190 of them are tiny, like less than a few megabytes each.
It fixes it.
It fixes it. AQE will automatically merge those many small partitions into a smaller number of larger, more reasonably sized partitions before the next stage starts reading them. This drastically reduces the file management overhead, improves downstream read parallelism and speed, and basically solves that too many small partitions problem without the user having to perfectly guess the spark.sql.shuffle.partitions value beforehand.
That's brilliant. It's like self-tuning partitions.
Pretty much. And third, AQE also significantly helps in dynamically mitigating data skew during shuffles and joins. If AQE detects that certain tasks are taking much longer than others during a shuffle read phase, indicating a skewed key, it can sometimes intervene. It might automatically try to split up the work for that skewed partition, maybe by applying some kind of internal repartition or even a form of salting automatically to redistribute the processing of that heavily skewed key across multiple tasks, thus reducing the impact of the straggler. It's the system actively trying to fix data skew problems while the job is still running. It's a really powerful set of features.
We've talked a lot about execution plans and shuffling data around, but the actual format you store your data in, that's another massive lever for performance, right? Why should users almost always prioritize structured columnar formats like Apache Parquet or ORC over, say, older unstructured flat files like CSV or JSON?
Oh, the difference is absolutely night and day. Using columnar formats fundamentally changes the I/O cost and enables optimizations that are just impossible with row-based formats like CSV. Well, think about a CSV file. It's just text, row by row. If you want to read just one column from a CSV file that has 50 columns, you still have to read every single byte of every single row from start to finish, parse it, and then discard the 49 columns you don't need. It's incredibly wasteful.
Right. You read everything just to throw most of it away.
Exactly. Now contrast that with Parquet or ORC. These are structured binary formats where the data for each column is stored together, contiguously. This columnar layout allows Spark to exploit two key optimizations far more effectively. Predicate pushdown, which we discussed for filtering rows, and projection pushdown.
Okay, breakdown, projection, pushdown. How does that work with columnar formats?
So imagine your Parquet file has those same 50 columns, but your query only actually needs 2 of them, maybe client name and order total. Because the data is physically stored column by column on disk, projection pushdown enables Spark's reader to go directly to the disk blocks that contain only the data for client name and order total.
It just skips reading the other 48 columns entirely.
It completely skips reading the physical data blocks for the other 38 columns. It doesn't even pull them off the disk. The research we looked at and practical benchmarks consistently show that reading only the required columns via projection pushdown can reduce I/O latency and data volume, read by anywhere from 50% to even 75% or more, depending on the width of your schema and how selective your query is.
Wow.
You save disk bandwidth, you save network bandwidth reading from cloud storage, you save memory consumption in the executors because you're loading less data, and you save CPU processing time because you're deserializing and processing less garbage. It's just a massive win across the board. Always use columnar formats for analytical workloads.
Okay, that's a clear directive. Now moving into the broader ecosystem surrounding Spark, platforms like Delta Lake, which add transactional capabilities and other features on top of Parquet, offer even more advanced data bending capabilities beyond just simple partitioning. How does Z-ordering work within Delta Lake to improve query performance? Sounds fancy.
It is pretty fancy and quite effective. Standard partitioning, as we said, is good, but it's inherently one-dimensional. You partition by date, you optimize reads that filter on date, you partition by country, you optimize for country filters. What if your queries often filter on multiple columns?
Right, like where date equals and country exists.
Exactly. Z-ordering is a multidimensional clustering technique designed for that. It uses a mathematical concept called the space-filling curve, often the Z-curve, hence the name, or sometimes a Hilbert curve, to try and collocate data points that are close to each other across multiple specified columns, say region and customer, into the same physical Parquet files within your Delta table.
So it's trying to keep related data physically together, even across different dimensions.
Precisely. It maps multidimensional data points onto a one-dimensional curve in a way that preserves locality as much as possible. The benefit is improved data skipping. If you then run a query that filters on both region and customer range, like where region east and customer between 1,000 and 2,000, the Z-ordering metadata allows Delta Lake and Spark to potentially skip reading vast swaths of files because it knows those files cannot possibly contain data matching both predicates simultaneously.
So it's like supercharging your predicate pushdown from multi-column queries by physically organizing the data better.
That's a great way to put it. It works alongside partitioning to provide finer-grained data skipping within partitions.
And what about the newest concept mentioned in the sources, liquid clustering? What problem is that trying to solve that maybe Z-ordering or traditional partitioning couldn't fully address?
Liquid clustering aims to tackle the rigidity problem inherent in both traditional partitioning and Z-ordering. With both of those techniques, you have to choose your partitioning or Z-order columns up front when you create the table or run the optimization command.
Right, you commit to a strategy.
Limit. But what if your query patterns change over time? Maybe users start filtering on a different column more frequently. With partitioning or Z-ordering, if you want to optimize for that new pattern, you typically have to perform an expensive operation to completely rewrite the entire dataset, repartitioning or re-Z-ordering it based on the new keys. That's costly and time-consuming.
Okay, so liquid clustering is more adaptable.
That's the goal. It's designed to be a more flexible, incremental approach to data layout optimization. The idea is that the clustering strategy can evolve over time, perhaps based on analyzing recent query workloads, without necessarily forcing a complete disruptive rewrite of the entire table every time you want to adjust the layout. It aims to optimize data layout more continuously and adaptively as data grows and access patterns shift. Still relatively new, but addresses a key pain point of static optimization strategies.
Very interesting. Okay, now we arrive at the ultimate frontier, perhaps, of Spark automation. We established early on that manually navigating those 180 plus parameters is practically impossible for achieving true optimal performance. So what systematic, maybe even ML-driven approaches are necessary to even hope to find that near optimal configuration?
Yeah, at this point, you absolutely must turn to automated scientific search methods. Trying to find the best configuration through just manual trial and error, or even a basic grid search where you try a few values for a few parameters, is just computationally prohibitive. The parameter space is way too massive and complex, with interactions between settings.
So simple guessing won't cut it. What techniques do work?
The state-of-the-art approaches generally employ techniques like Bayesian optimization or sometimes genetic algorithms. These are used within a continuous feedback loop. You run the Spark job with a configuration, measure its performance, feed that result back into the optimizer, which then intelligently suggests the next configuration to try.
Why is Bayesian optimization specifically often mentioned? Why is it better than just trying random combinations or a grid search?
Because it's an intelligent search, not a brute force one. Grid search naively tries every combination you define. Random search just picks points randomly. Bayesian optimization, however, builds a probabilistic model, a surrogate model, of the performance landscape based on the results it has seen so far.
Okay.
It uses this model to predict which unexplored configurations are most likely to yield the greatest improvement over the best result found so far. It balances exploring unknown areas of the parameter space with exploiting areas known to be good. This allows it to focus the search much more efficiently on the most promising configurations, often finding a near-optimal setup in significantly fewer runs, saving time and money, compared to exhaustive or random methods. It's particularly powerful for tuning those complex low-level parameters like JVM settings, heap sizes, GC algorithm parameters like G1GC settings, where human intuition completely fails.
And what data actually feeds this machine learning optimizer? The source is referred to an oracle model. What is that?
The Oracle model is essentially that surrogate model I just mentioned, the ML model trained on the performance results. To train it effectively, you need detailed execution metrics. So you run some initial Spark jobs with varying configurations, and you meticulously capture the highly detailed Spark event logs.
Those logs contain more than just job finished.
Oh, much more. They're incredibly rich data sources. They capture detailed timings for stages and tasks, CPU usage metrics, network I/O bytes read-written, shuffle statistics, bytes read-written records, memory usage, and critically detailed garbage collection metrics, frequency, duration, type of GC events.
All the nitty-gritty details.
All the nitty-gritty. The ML model, the Oracle, trains on this detailed data. It learns the complex relationship between input configuration parameters like executor memory, shuffle partitions, compression codecs, etc., and the resulting performance outcome, usually total execution time.
So the oracle essentially learns to predict, okay, if you give me this specific set of configuration values, I predict your job will take approximately 45 seconds to run. And that prediction guides the Bayesian optimizer towards better and better suggestions.
That's exactly it. This predictive capability is what saves potentially weeks or months of manual, painstaking trial and error tuning. However, even with this incredibly sophisticated ML-driven automation, we slam into the final and perhaps most frustrating challenge in performance tuning: high runtime variance.
High runtime variance. What does that mean for the poor data bender who thinks they've finally found the perfect optimized configuration using their fancy Bayesian optimizer?
It means frustration. It means that due to all the inherent noise and non-determinism in a complex distributed environment, things like slight variations in network latency, jitter, operating system scheduler decisions on the nodes, temporary resource contention from other processes, maybe even cloud provider noisy neighbor effects, running the exact same Spark code with the exact same optimal configuration multiple times in a row can yield significantly different execution times.
So run #1 takes 50 seconds, run #2 takes 55 seconds, run #3 takes 48 seconds, all with the identical setup.
Exactly. You might run your new optimized configuration and find it finishes in 47 seconds. Compared to the baseline of 50 seconds. You think, great, a 6% improvement. But was it? Because of the runtime variance, that 47 seconds might have just been a lucky run. The true average performance might actually be 51 seconds, meaning your change made things worse.
Oh, wow. So how do you prove an improvement is real?
You have to resort to statistics. You need to run both the baseline configuration and your supposedly improved configuration many times, sometimes dozens of times each, just to gather enough data points to statistically prove, with confidence, that the observed difference in average performance is actually real and not just random noise or a statistical blip.
That sounds incredibly expensive and time-consuming, just to confirm a small gain.
It is. This challenge adds significant computational cost and methodological complexity just to validate that your optimization efforts were successful. It requires real scientific rigor-controlled experiments, statistical tests in an environment where often speed of development and deployment is also critical. It's a tough balancing act.
That is a really powerful point, and it perfectly encapsulates the whole optimization journey, doesn't it? It's complex, multi-layered, and even when you think you're done, there's still uncertainty. We've covered so much ground today, from really understanding the physical plan that Catalyst creates through lazy evaluation, all the way to using machine learning to guide cluster configuration.
Yeah, and if there's one core takeaway for you listening, it's this. True Spark mastery really means moving beyond just the high-level coding syntax of Python or Scala functions and digging in to truly understand how Spark plans to execute that code. You need to learn to read the physical plan.
Know what it's actually doing under the hood.
Exactly. Master the shuffle, minimize it, configure it right. Strategically apply those broadcast hints, but be careful. Leverage the dynamic power of AQE to let Spark fix things on the fly, and embrace systematic automated configuration tuning because manual tweaking just doesn't scale. By learning to read and influence the physical plan, you stop just reacting to slow performance after the fact, and you start proactively architecting for fast performance from the beginning.
By doing that, you really do transform from being just a casual Spark user into, well, a master architect of distributed computation, a true data bender.
Nicely put. And this brings us right to our final provocative thought for you to chew on. We've seen how even when we employ these highly advanced machine learning techniques for automated tuning, we're still constantly battling this fundamental problem of high runtime variance. So the question becomes, if rigorously proving even a modest performance improvement, say 5% or 10%, requires dozens of expensive time-consuming repeated runs just to be statistically confident, when does the financial cost, the computational cost, and the engineering time cost of pursuing that last bit of optimization actually stop being worth the practical return? Where's the point of diminishing returns in the real world?
That's a deep question about the economics of optimization itself, something to definitely ponder.
It is. So remember, in the world of big data, true mastery isn't just about writing the code. It's about learning how to bend the execution plan to your will. Now go forth and conquer the shuffle.